Good morning everyone, I am Mr. Reverend Eduardo Bertido from BSTE 5A. I am here to report our topic in industrial plant with water treatment, and I would like to tackle first the removals of acids and alkalis. The alkalization of water refers to the removal of alkalinity ions from water. Chloride cycles anion-ion exchange. The alkalizers remove alkalinity from water. Acids and alkalis can usually be neutralized under controlled conditions. New neutralization frequently produces a precipitate that will require treatment as a solid residue that may also be toxic. There are two components that have been used to neutralize acidic solutions that are sodium hydroxide and calcium hydroxide. Treatment is by concentration of the ionization waste waters and disposals to landfill or by careful pH management of the released wastewater. Acidic water is neutralized using ammonia or soda ash. Alkaline wastewater is treated with sulfuric acid, carbon dioxide, rice flue gas, or sulfur. How to neutralize acidic well water? First step, test your well water for at least pH, alkalinity, hardness, total dissolved solids. Use a calcite neutralizer to eliminate the acid pH. And then use a blend of calcite and magnesium oxide or Corosex or Plumag brands and etc. for very low pH. Use a backwash type neutralizer or an upload neutralizer, depending on your application and water. And last step is consider a soda ash injection system if your pH is 5 or below and or your water is high in calcium.
The definition of acidic water has to do with the level of pH. And pH is a scale of acidic or alkaline water from 0 to 14. 7 being right in the middle, that's considered neutral. Anything below neutral is on the acidic side of the pH scale. And acidic water can be quite corrosive. Anything above 7 on the pH scale is considered alkaline. And quite frankly, there's a lot of health folks out there talking about how high pH water is actually better for you. But today we're going to talk about taking care of water that's on the acidic side and what we need to do to move it back towards neutral. Water becomes acidic basically because in the hydrologic cycle, when water evaporates and condenses in the sky to create clouds, and then those clouds get full of moisture and it precipitates back to Earth, either as rain or snow. In that process of precipitation, water combines with carbon dioxide and creates carbonic acid. So rain is slightly acid. And depending upon the Earth that it goes down through into our groundwater, it can become either higher in pH because it passes through alkaline-rich rock in the soil, or it can actually become more acidic due to the lack of those kind of minerals being in the soil. Well, when that happens, we need to do something to adjust that pH, adjust that acid water back up towards neutral. The reason that we do that is because acidic water can be very, very corrosive. By golly, if you have acidic water, you want to treat the whole house because that acid water is destroying all your plumbing. If you are seeing blue or greeny stains on your drains, that's what you've got going on. You've got acidic water that's actually eroding the copper from the inside of your plumbing. And if that's left unaddressed, what happens next is you'll get pinhole leaks. And you know Murphy's Law, those pinhole leaks are going to be behind a wall someplace and you're going to have lots of damage to repair. So acidic water is something not to be toyed around with. You definitely want to make sure that you take care of it. It can also destroy your water heater or any of your hot water using appliances. The hotter the water is, actually the more corrosive that water becomes. There's a number of ways that we attack acidic water. The most common is using a material called calcite and flow water through that calcite to raise pH. Calcite is a mineral that's very high in alkalinity. In fact, it's made a lot of calcium, and calcium is very rich in alkalinity. And by passing water through that, and keep in mind, water is a universal solvent, and as water touches stuff, it dissolves it, and then it carries away and it becomes part of that water molecule. As we get calcium and alkalinity rich mineral back into that water molecule, pH raises. And that's the easiest way to raise pH and make it neutral. When we use calcite, we understand that calcite has some basic limitations. It is very, very dependent upon how much contact time the water has with the mineral. So the farther that we need to raise pH, the more we have to understand the limitations of what calcite can do. Typically, calcite can move pH 1 point. So if we're between 6 and 7, remember 7 is neutral, if we're between 6 and 7, calcite may get us there. So we've got to make sure we have enough calcite based upon our flow rate requirement to move pH that 1 point upwards. So the amount of calcite is going to be directly linear to how much flow rate we have. And that's calculated out in our spec sheets and so forth. Now, if we have acidic water that is more than 1 point away from neutral, say 1.5 away, then we're going to use an additive to the calcite, and it's a mineral called Corasex. Actually, it's magnesium oxide, and it has the ability to really adjust pH, but we don't want to use a lot of it because it can actually overcompensate. Plus, on the side, it's magnesium, and too much magnesium in your water can act as a laxative, and you probably don't want that. So calcite's good for 1 point. We add a little Corasex if we got to raise it 1.5. If we are in low 5s, or we're even looking at acidic water that's in the 4s on the pH scale, we're probably going to go to a different type of pH adjustment. The first step beyond calcite would be chemical injection using a product called soda ash. Now that's a maintenance problem. It's very difficult to deal with. You've got to be very committed to it, but if your water is that acidic, you would be. And if it's too far for soda ash to move, if we actually get down into the low 4s, we're going to use caustic soda. Caustic soda is incredibly alkaline at a 14, and it's about the only material we can use to move pH far enough to get it neutral when we're down that low.
And now, let's tackle about the removals of toxic materials or leachate treatment. Toxic materials including many organic materials, metals, acids, alkalis, non-metallic elements are generally resistant to biological process unless very dilute. Leachate is any liquid that, in the course of passing through matter, extracts soluble or suspended solids or any other components of the material through which it has passed. There are some conventional methods to remove toxic materials. First, we will tackle about our precipitation. Precipitation is the most common method for removing toxic heavy metals up to parts per million levels from water, since some metal salts are insoluble in water and which get precipitated when correct anion is added. Although the process is cost effective, its efficiency is affected by low pH and the presence of other salts. The process requires addition of other chemicals, which finally leads to the generation of a high waste content. Sludge, the disposal of which is cost intensive. Precipitation with lime or ion exchange lacks the specificity and is ineffective in removal of the metal ions at low concentration. And now, let's tackle about the ion exchange. Ion exchange is another method used successfully in the industry for the removal of heavy metals from effluents. Though it is relatively expensive as compared to other methods, it has the ability to achieve ppb levels of cleanup while handling a relatively large volume. An ion exchange is a solid capable of exchanging either cations or anions from surrounding materials. Commonly used matrices for ion exchange are synthetic organic ion exchange resins. The disadvantage of this method is that it could handle concentrated metal solution as the metric gets easily fouled by organics and other solids in the wastewater. Moreover, ion exchange is non-selective and is highly sensitive to pH of the solution. And now, let's tackle about electrowinning. Electrowinning is widely used in the mining and metallurgical industrial operations for heap leaching and acid mine drainage. It is also used in the metal transformation and electronics and electrical industries for removal and recovery of metals. Metals like gold, silver, present in the effluents can be recovered by electrodeposition using insoluble anodes. Electrocoagulation is an electrochemical approach which uses an electrical current to remove metals from solution. Electric coagulation system is also effective in removing suspended solids, dissolved metals, tannins, and dyes. The contaminants present in the wastewaters are maintained in solution by electrical charges. When these ions and other charged particles are neutralized with ions of opposite electrical charges provided by electrocoagulation system, they become destabilized and precipitate in a stable form. And next is the cementation. Cementation is a type of another precipitation method implying an electrochemical mechanism in which a metal having a higher oxidation potential passes into solution. Example, oxidation of metals into ferrous. To replace a metal having a lower oxidation potential, copper is most frequently separated by a cementation along with noble metals such as gold and silver. Next is the reverse osmosis and electrodialysis. It involves the use of semi-permeable membranes for the recovery of metal ions from dilute wastewater. In electrodialysis, selective membranes or alternation of cation and anion membranes are fitted between the electrodes in electrolytic cells and under continuous electrical current associated. So, let's go further. There were also technologies to treat toxic or leachate materials such as smart capsule, biological wastewater treatment, mechanical treatment by ultrafiltration, treatment with active carbon filter, electrochemical treatment including electrocoagulation, and reverse osmosis membrane filtration. Let's tackle first about the smart capsules. Molecular encapsulation is a technology that has the potential to provide a system for a recyclable removal of lead and other ions from polluted sources. Nano, micro, and milli capsules are particles that have an active reagent surrounded by a carrier or shell. There are three types of capsule under investigation. First is the alginate-based capsules, carbon nanotubes, and polymer swelling capsules. And next is the biological wastewater treatment. Biological wastewater treatment is a process that seems simple on the surface since it uses natural process to help with the decomposition of organic substances. But in fact, it's complex or not completely understood process at the intersection of biology and biochemistry. Biological wastewater treatment harnesses the action of bacteria and other microorganisms to clean water. Biological treatments rely on the bacteria and nematodes, or other small organisms, to break down organic waste using normal cellular process. The goal of biological wastewater treatment is to create a system in which the results of decompositions are easily collected for proper disposal. Biological treatment is used worldwide because it's effective and more economical than many mechanical or chemical processes. Biological treatment usually is divided into two processes. First one is the aerobic. Microbial reaction takes place in the presence of molecular or free oxygen. Reactions products are carbon dioxide, waters, and excess biomass. Wastewater with low to medium organic impurities or chemical oxygen demand is less than 1,000 parts per million, and for wastewater that are difficult to biodegrade, example of this is the municipal sewage and refinery wastewater. Next is the anaerobic. Microbial reactions takes place in the absence of molecular free oxygen. Reaction products are carbon dioxide, methane, and excess biomass. Wastewater with medium to high organic impurities or COD greater than 1,000 ppm and easily biodegradable wastewater. Example is food and beverage. So now let's talk about its biological process. First, the bacteria is attached to the filter media forming a biological layer called biofilm. Then, sprinkled wastewater over the filter media forms liquid film including food and dissolved oxygen. The bacteria or biofilm absorbs the organic matter and oxidizes it, producing water, carbon dioxide, and new cell. The biological layer consists of aerobic and anaerobic portions. And the last is, when the mass of the biofilm increases, the lower layer will be anaerobic, with lower food supply, which will be lead to decrease of the attaching force between the biofilm and the media. In this case, the biofilm slowed out or disconnected and flows out with the wastewater to the final sedimentation tank where it settles. And for more details, just watch this video.
Outside in a black drop, 10 rolled up in a mouth. Say they all wanna live.
Technologies that can treat the toxic materials in the wastewater is the mechanical treatment by ultrafiltration. Ultrafiltration device or UF device are used to recycle and reuse water that contains virtually no physical solids. Ultrafiltration is a variety of membrane filtration in which forces like pressure or concentration gradients lead to a separation through a semi-permeable membrane. Suspended solids and solutes of high molecular weights are retained in the so-called retentate while water and low molecular weight solutes pass through the membrane in the permeate. Ultrafiltration can be used for removal of particulates and macromolecules, so it will be removed from raw water to produce potable water. Ultrafiltration is an effective means of reducing the salts density index of water and removing particulates that can foul reverse osmosis membranes. Ultrafiltration is often integrated into two processes using primary or screening, flotation, and filtration, and some secondary treatments as pre-treatment stages. Ultrafiltration processes are prepared over traditional treatment methods for the following reasons. First, no chemicals required aside from cleaning. Next is the relatively cheap, compact plant size, capable of exceeding regulatory standards for water quality or achieving 90 to 100% pathogen removal. Constant product quality regardless of feed quality. And to understand more about this topic, just watch this video.
Ultrafiltration system at St Mary's uses hollow membrane fibers to remove suspended solids, bacteria and viruses from the tertiary treated wastewater. Each membrane fiber has millions of microscopic pores. Each pore is about 0.02 of a micron in diameter. A human hair is about 75 microns in diameter. These membrane fibers sit in cells filled with tertiary treated wastewater, also called feed water. Pumps draw the filtered water or filtrate through the microscopic pores into the fibers themselves. The pores act as a physical barrier. Only filtrate can pass through the pores. Unwanted materials, suspended solids, bacteria, viruses and pathogens like Cryptosporidium and Giardia are left behind. The membranes are arranged horizontally into modules. Each module contains 30,000 membrane fibers held by resin at each end. The membrane fibers connect to a single common module header. This is where the filtrate is collected. Two plastic shrouds encase the sides of the module. The shrouds protect the fibers and draw the feed water upward through the modules. 3 membrane modules are loaded vertically to form a stack. Each stack has its own filtrate collection pipe. This design limits the number of individual connections in the system. There are 16 stacks, or 48 membrane modules, loaded into one cassette. A cassette is an assembly of membrane stacks. There are 4 cassettes arranged in one cell. There are 6 ultrafiltration cells. The design maximizes filtration efficiency. Tertiary treated wastewater from the feedwater balance tank is pumped to the ultrafiltration strainers. The ultrafiltration strainers remove solids, such as weeds and plastics, from the wastewater before it enters the ultrafiltration system. Stack collection pipes carry the filtered water, or filtrate, to a single manifold header on the top of each cassette. Feedwater is continually pumped to maintain a constant level in the cells. The St Mary's ultrafiltration system produces 58 million litres of filtrate every day. This filtrate is then sent to the reverse osmosis system for further treatment. After a period of operation, the fibers become blocked by the retained particles. This restricts the flow of water. The fibers are cleaned through cycles of backwashing and chemical cleaning. Backwashing pushes some of the filtrate through the manifold header into the cassettes and through the membrane pores to dislodge any stuck material. The backwash cycle removes particles blocking the membrane fibers. The backwash cycle occurs every 20 to 30 minutes in one cell at a time to allow the other cells to continue working. In addition to backwashing, chemical cleaning cycles remove any material still stuck to the membranes. Each cell is drained and its membranes are soaked in a cleaning solution for several minutes. This solution is then drained and flushed from the cell before the regular ultrafiltration cycle begins again. Chemical cycles occur every 24 hours in one cell at a time. The used cleaning solutions are treated and returned to the start of the wastewater treatment plant. along with the removed materials and contaminants.